sept analysis results from a sept test, from hydrometry test, is that we got a particle size distribution curve that is a curve like this. You see from here, actually, we say that sept analysis is for big particles, and hydrometry analysis for particle size less than 0.075 millimeter. So this part, the triangle in here is obtained from a hydrometry analysis, and the sept analysis will obtain the points in the left part. If you want to got total particle size distribution curve from large particles to very fine particles, you need to conduct both tests. But if you just want to get a chaos particle size distribution curve, sept analysis actually is enough for this. In most cases, we just need to do the sept analysis to go to the important part. That's this part, actually, the sept analysis. From sept analysis, you go to the silt and you go to the sand particle range, right? The percentage of silt and sand, and then you can go to the clay, because in most cases for a soil we study in laboratory, usually we have already this kind of soil is not gravel anymore, actually. So 100%, as long as you got silt percent and sand percent, then you got clay percent. But if you want to go to beautiful or a whole particle size distribution curve, it's better to conduct both tests. And then you connect them together, because you see the joint part in here is not always consistent. So just try to connect them together, got a float curve, nice curve, that's all. Yes?
Sorry, the percentage, right? On plus like, does the percentage, like when you are shaking, when you put the soil in the sea, right? When you are shaking, the more you shake, the more they collide.
No. No, as long as you didn't push the particle. You shake 15 minutes, that's actually enough for all those particles to pass the opening. If the particle is bigger enough to retain on the seed, even you sieve for a very long time, because it's big, it can't pass the opening.
But they will break. They will collide with each other and they will break.
No. The sieve is just a sieve. It's not like you. Yeah, that's not one particle. That's how to say. That's the stick particle. Stick together. As long as you can shake them into two pieces, that's two particles, right? So actually, in here you just follow the code. Yes, maybe if you sieve for half hour or 1 or 2 hours, the percentage may be changed, but not too much. 15 minutes is enough. Yes, maybe particle will break, but the sieve will not, how to say, it's not strong enough. It's just strong enough to let those particles pass those openings, but not strong enough to break a particle. Like this, but as long as it can break, it is two particles, not one particle.
So the shaking is more like a vibration. It doesn't really shake.
It's a shake. It's shake. It is shake. It's like you have base, right? And then you put the pile of sieves on the base. Then you start the machine. The base is shake. But the shake is not very, very strong. It is just a shake. Yeah, a frequently shake. Before the machine, people shake with hands. Yes, I do this in laboratory. The hand is also work. As long as you think that you shake, the particle the mass didn't change anymore, then you think that is enough. So actually, in most cases, we have a code. If people follow this code. So it's actually, it doesn't matter, right? And then we go to the particle size distribution curve. In here, in most analysis, as long as you got the particle size distribution curve, what we need to do is to define the soil, to classify the soil. If the soil is a clay, silt, or sand, or it is a silt clay, or a sandy silt, so different types of soil. You need to define it, give it a name, right? So now you need to calculate how much percent of clay, how much percentage of the silt, and how much percentage of sand. And when we calculate this, you need to have a code. For example, we list some in here. We list some in here, right? You see, because the distinguished particle is different. It's different. So follow different code. Different code will give you different results. Even the results looks similar, but sometimes they are quite different. So as long as you do the analysis, or you say the silt is how much percent silt, how much percent sand, how much percent, you should say you follow what kind of code. For example, in here, let's say we follow the USD department or USDA. We follow the USDA code to do the analysis. If we follow this code, let's say this code to do the analysis, to calculate the percentage of clay, silt, and sand, then the clay is the particles at less than 0.002, right? So you find the 0.002 in the particle size distribution curve, and the y-axis is about in here, right? This is the percentage. This gives you the percentage of the clay, right? So the clay is about 12%. And with the same way, we need to find the percentage of silt particles. Silt particle is about 0.002 to 0.075. Then 0.002 is in here. 0.005, it is in here. Well, 75 is in here. So this particle, this distinguished particle, the occurrence percentage is about in here. So the silt actually, you see, the 61 in here is the accumulated percent. So it actually accounts for the percentage of the particle less than 0.075. And it included the clay particle. So, right, in here, if you want to calculate only silt particle percentage, you need to minus the clay particle percentage, okay, right? Because we said that the y-axis gives you the accumulated percentage. So the silt actually is 61 minus 12, it is about 49%. And if follow this code, ask you to find the sand particles, it is 0.075 to 2 millimeter. So 2 millimeter is about in here. And the sand then accounts for, this y-axis is about 98, right? 98%. But the 98% include what? Sand, silt, and clay, right? So you need to use the 98% to minus silt and clay. Then you got the percentage of sand, right? And the final gravel is the last 2%. So this is the analysis from the particle size distribution curve. As long as you got the curve from a sieve analysis and hydrometer analysis, then you can analyze how much clay, how much silt, how much sand and gravel included or contains in the soil, right? This is the kind of analysis. But before doing this, you need to say you followed which code you followed, right? If we change to this, the results may be changed, right? If you follow this code, the results will change. And this is the first thing that we can do with the particle size distribution curve. And then we can also analyze the uniformity of a soil from the particle size distribution curve. So with particle size distribution curve, we usually can define two different coefficients. Three. The first one is effective size, D10. What's that? The D10 is actually tells you the particle size according 10% on the particle size distribution curve. The same, we can go to D30 and D60. 10, 30, 60 in here is the percentage. So just go to the y-axis, find the 10, 30, 60, the accordance. X-axis is the particle. That for particle size, that for D10, D30, D60, right? So D10, D30, D60 is a particle size, it's not a percentage. And the 10, 30, 6 in here, it is the percentage. Understand? This is some effective size we defined in here. Why we define this effective size? Because with those effective size, we can calculate the uniformity coefficient and the coefficient of gradation. So we define Cu, the uniformity coefficient is the ratio between D60 and D10. And the coefficient of gradation, Cc, can be calculated with D60 and D30, D60, and D10. Right? Then why we calculate Cu and Cc? You see, it is called uniformity coefficient and coefficient of gradation. Why we calculate these two? Because these two coefficients, Cc and Cu, can help us to analysis if the soil is uniform or not, if the particle size distribution is very nice or not. So this is why we calculate these two. But if you want to calculate these two coefficients, you need to know D10, D30, and D60, right? And the D10, D30, D60 are diameter of particle corresponding to a percentage of 10, 30, 60 on the particle size distribution curve. So as long as you know Cu and Cc, then you can analyze if the soil is a well-graded, polygraded, and gap-graded. So the polygraded soil is a soil where most of soil grains are the same size. For example, this. You see, the curve looks beautiful, but it missed the particle larger than 0.05, right? And missed the particle larger than maybe 0.60, 0.7, right? a polygraded because you see, particle range is only from 0.05 to maybe 7, right? So it means that the particle size range less than this and higher than this. It is only the particle size only distributed in such a small range. So we say this is a polygraded soil. A good soil or a well-graded soil is a soil where the particle size are distributed over a wide range. For example, this one, the second one, the two in here, the well-graded. It is, the particle size is from about 1.2 or 1.3 to here. 0.0, maybe 0.18, right? It is in a much larger range. It contains more different particles, different particle size. The range of the particle size is large, right? This is a well-graded soil. So a gapped soil, what is a gapped soil? A gap-graded soil is a soil which has a combination of two or more uniformity graded refraction. This is the third curve in here is a gapped graded soil. Why we say it is a gapped? Because you see, from here, maybe it is 0.06 to here, 0.15, let's say it's 0.40. For this point of range of particle, you see the percentage almost didn't change, or the change of the percentage is very small, right? That means this range of particle size almost missed in this soil. There is no much particles in this range, right? This is why from here to here, the percentage, if we say from here to here, for the particle from this size to this size, the percentage almost didn't change. That means the mass for particle in this size range have not much, right? This is why the percentage is very small. The percentage change is very small, just from here to here, right? Very small. So let's say that the soil, for this kind of soil, the soil missed some of the particle range, right? So this is a gap-graded soil. That is like that the soil was gapped in some range of particle size. In most cases, so it is actually difficult to define this just with your eyes to see the particle size distribution curve. So we use the CU and CC to define if a soil is a well-graded soil or polygraded soil. Let's say for a gravel, if CU is higher than 4, we say it is a well-graded soil. And if for sand, if CU is higher than 6, we say it is a well-graded soil. And a well-graded soil is not only depends on CU but also CC. So if CC is between 1 to 3, we say this kind of soil is a well-graded soil. So as long as CU and CC meets these requirements, then it is a well-graded soil. So if you want to define a soil if it is or not a well-graded soil, you need to calculate CU and CC. But if you want to calculate these two, you need to know D10, D30, and D60. And if you want to got these 3 particle size, then you need to got a particle size distribution curve, right? And you need to conduct a sieve analysis or Hartrowitz analysis, right? So step by step. Then let's see particle shape. Particle shape, the 3 major categories of particle shape are Barclay particles. flatly particles and needle-shaped particles. Let's see. What's these particles? The particles in different shape. So while we study particle shape, now particle shape is already a branch, a research branch in soil mechanics, because different particle shape, when those particles get together, actually it will cause a different shear strength. Sometimes particle breakage. If you put those particles together, the breakage rate is small, but the shear strength is also small, right? But if you put those kind of particles together, when you apply a shear load, actually those particles can, can stop one by one to shear failure, right? But during this time, those kind of particles, because it have an edge in here, a sharp edge in here, it's easy to be break. So you need to analyze the breakage during some load, during compression, during shearing. So this is particle shape, but it is not the main thing in soil mechanics for undergraduates. So we finished chapter 2 actually. We discussed the origin of soil and rock cycle in chapter 2 and different of rocks, the weathering, chemical transportation of weathered products, and also sedimentary rocks and metamorphic rocks. We introduced particle size and specific gravity. We provide a foundation of clay minerals, discussed the type of mechanical analysis that can be done on soil, sieve analysis and hydraulic analysis, and then how to analyze a soil with particle size distribution curve, right? So this is contents we discussed in chapter 2. Yes, we're done in chapter 2, and then let's see some examples for the mechanical analysis of soil. Let's see an example. We've already introduced the opening of the sieve, right? The opening actually, finally, it is the particle size in the x-axis, right? If we want to obtain a particle size distribution curve. And after sieve analysis, as long as we got the mass on each different sieve, then with this equation, we can calculate the accumulated percentage of particle, right? And M is the mass of soil retained on each sieve. Sigma M is the total mass of soil. And finally, as long as we got the percentage on the y-axis and the particle size, depending on the opening on the x-axis, then we can curve the particle size distribution. Let's see the example. 2.1, it is an example on our textbook. It is actually a typical example. So the following are the results of sieve analysis. So you imagine that you have done the sieve analysis in laboratory and you know the sieve number and you know the mass soil retained on each sieve. We can absolutely do this, right? And based on those results, ask you to perform the necessary calculation and plot a grain size distribution curve or a particle size distribution curve. You need to plot the PSD curve. And then ask you to determine the D10, D30, and D60 from the grain size distribution curve and ask you to calculate uniformity and coefficient of gradation, Cu and Cc. So this is actually a core analysis we have done on this particle size distribution curve. But before we do this, the first thing is to plot the particle size distribution curve based on this result, right? So it is easy. Actually, in laboratory, when you're doing the sept analysis, you absolutely know the sept number, right? Because follow the code. For each laboratory, the sept number is the same. And it tells you this is a US sept number. As long as you know the number to check the US sept size with number designation, it gives you the number, then you can check the opening in here, right? The opening, we say the opening actually is the x-axis. Then you can got the number of the x-axis for each point on the particle size distribution curve. And you want to put up your hand. And then the mass of retaining on each sept mass is in here. With this equation, actually, we can calculate the percentage according to each opening, right, or each sept number, right? So finally, actually, we can got 1, 2, 3, 4, 5, 6, 7, 8. We can got 8 points on a particle size distribution curve, right? As long as we got this 8 point, you got the x and y axis number for this 8 points, and then plot those 8 points together, then you have got a particle size distribution curve, right? And with this particle size distribution curve, you can determine D10, 30, 60 from the grain size distribution curve. And finally, you can calculate Cu and Cc based on equation, right? So the main thing in here is actually to calculate the percentage according to different sept number, right? What?
Sorry, I have a question. So the total mass of the soil that was used, like the total all the figures in the mass in each seed.
The total mass.
Yes, also
So,
add all of them.
yes. Yes. In here. So as long as you know the sept number, you know the opening, right? Actually, you know the size of the particle. But you need to know the percentage of according to each size, right? So the percentage in here you need to calculate with this equation. But in this table, it just tells you MA on each sept, and didn't tells you the total mass. But the total mass actually is the sum of the mass on each sept, right? Right. So actually, we've already know everything. So what we need is to define those points on the particle size distribution curve. Actually, we need to know the diameter or particle size di. We need to calculate Fa, and we know that we have 8 points. Let's see how to define di and Fa. Di actually finds the opening of each sept number. This is a US sept. Sept size with number designation. And the problem in here gives you 4, 10, 40, 20, 40, 60, 100, 200, and 10, right? Then the opening of the sept number 4, 10, 20, 40, 60, 100, 200. The accordance opening is the particle size we want to find, right? This particle size is actually di in here. And how to calculate Fi, the percentage final Fi, then we need to use this equation. What you need to do is just to put those numbers in here, because it already gives you the MI on each sieve, right? So actually what we need to do is, step 1, we know the sieve number, right? And to find the opening for each number, for example, for 4, it is 4.75 millimeter. For 10, it is 2 millimeter, 20, 40, 60, 100, and 200. Finally, you got the accordance, the corresponding opening for each sieve number, right? You got the x-axis number. And then we know that the mass retained on each sieve, this is what we got from the question, right? From the problem. But in here, we need to calculate first the accumulated mass retained on above each sieve, because we need to use this equation, right? First, we need to calculate accumulated mass retained on a sieve. So for first, the biggest opening, the biggest size, actually, there is nothing retained on it, right? 0. There is no particle retained on the first sieve, on the sieve with the opening 4.75, right? So the accumulated mass retained on the biggest sieve actually is 0. But for the next one, it is 21.6. For the third one, it should be the accumulated. Then it should be this plus this plus this. It is 71.1. And for the fourth one, it is this plus this plus this plus this. It is 173.7. And again, you can calculate the accumulated mass above a sieve for the 5, 6, 7, and total mass. Understand? Really? Let's see your homework. Let's see what you will handle with your homework. You say you know this, right? You say you understand. And finally, as long as you know the accumulated mass retained above each sieve, then with this equation, you can calculate the percent of fire. You know this, right? This column gives you the accumulated mass retaining above each sieve. And the total mass is 450. Then you can calculate the percent fire, finally, right? And this is the opening. This is the opening. Or we say this is the particle size. The x-axis. This is the y-axis, right? Then you got 1, 2, 3, 4, 5, 6, 7 points, right? They are. This is the first one. Second one. No, this is we should use the opening, right? And finally, put them on this curve. And find the D10. It is 0.09 millimeter, and D30. It is 185 millimeter, and D60. It is about 0.41 millimeter. And with these three, you can calculate CU. And you can also calculate CC. finally, you can analyze if this is a well-graded soil, right? Because we said that if it is a well-graded soil, the CU and CC should meet some requirements, right? These two requirements, then you can define if it is well-graded soil.
So,
Yes.
so those figures that did already give everything. It's like we're just going. Seems like when we notice when we plot on the map or on the graph, we're just going to start estimating. That's an estimation.
You need to plot this in your homework.
Yeah, I mean those figures are they an estimation or are they definite figures?
I didn't get you.
Look at it. What is it?
Well, let's stop it here. I have class. I have foreign class for undergraduates, Chinese undergraduates. Because we haven't finished the example, so we can. I want to give you homework after this class, maybe after next one.
Thank you.
But please think about these examples. If you have any questions, we can discuss on next class. Okay? Because we have examination problem in here, and for the last grades, I didn't did very well in here. So because it is not an open examination, it is closed examination. So you definitely need to remember the equations and to know how to analyze those problems. I'll post those the PowerPoint on WeChat group.